actually born in California in Downey, so I moved when I was about 4. So I still come out from time to time. It's always nice to be back in sunny LA. It was about 40 in Chicago when I left, so I was not exactly happy to walk into 109-degree heat, but I don't know, I'll take it compared to freezing temperatures. So I work at UPTAKE. I am a principal architect, and we'll talk a little bit about what that means. I am the only person with the title principal architect at UPTAKE. So it's a subject of much curiosity, and I know that's a really overloaded term in this business. So I came into that role, I would say, over time, really inspired by this man. So Brian Kernighan wrote a book called Software Tools in 1976. And this quote is attributed to him. It's actually from this book. I tracked it down. It took me quite some time to track this quote down. But I found it fascinating because throughout my career, I'd done a lot of work in what I was thinking of at the time as complex systems. And I'll touch a little bit on what the difference is between a complex adaptive system and a merely complicated system a little bit later into the talk. Whether we're talking about complexity or complication, where he was going with this is how to structure systems in such a way that you can actually understand them, that you can actually extend them over time, that you can hopefully be successful in delivering them. So I've worked at quite a few places where complex and complicated systems are known to exist. My first, quote-unquote real job was at Lockheed Martin. I worked on things like the automated fingerprint identification system. I worked on a asset entry simulator for the space program. And did some other cool stuff there, but this is around the time when ThoughtWorks was doing some really interesting things in the agile space. So early 2000s, I'd introduced cruise control to Lockheed, which was an interesting endeavor, and decided like, hey, well, ThoughtWorks is writing. These guys at ThoughtWorks are writing, all these books that I'm reading. Why don't I just go work there and just go work directly with these folks? So I did that, and I was at ThoughtWorks for a few years. You met my wife earlier, Sarah Eslanifar. I met her while working at ThoughtWorks, so I got a great deal out of that. Got a fun career and a wife. Who can say that? And then left there, went to DRW Trading, which is where I learned to go all in. See, that came in handy. Left there, went into the startup world. So I worked for a company called Aurelius for a little while. We shipped a database called Titan that you may or may not have heard of. It's in the graph space. Did a couple of smaller startups. One was called Outpace. That was some former DRW folks, some former ThoughtWorks folks, former McKinsey folks. Went from there to my own company. Sarah mentioned Tested Minds. So we were doing a lot of different projects, most of them in the closure space or in the health space. And then I landed at UPTAKE. The Tested Minds work, and this goes back to, again, that nature of complex adaptive systems versus merely complicated ones. This is Dr. Sri Sarma. I met her a couple of years ago. She works at the Johns Hopkins Institute for Computational Medicine, and she has an interesting background. She has a PhD from MIT in electrical engineering, but she had sort of minored in neuroscience, right? So she got really interested in treating the brain like an electrical system and applying control systems theory to the brain. And she introduced me to some work she was doing where she had built a prototype in MATLAB and had done some initial validation on an approach to treat a certain type of epilepsy. And her ask was, can you get this thing into a clinical setting? Because I want to take this to the next level and have people start doing clinical studies with this thing, doing side-by-side comparisons with patients. So that was interesting, teasing apart a MATLAB monolith. One of the first times I could say I had to do that. But we did some cool work there. And for those of you who may be queasy, I know we're after lunch, so this is not totally a graphic slide, but it's evocative, I will say. Some of our work's going to appear in a journal called Network Neuroscience, and the essence of it is this. The type of epilepsy that she's focused on involves certain regions of the brain that are basically misfiring, right? They're just sending out signals that cause a cascade and eventually turn into a seizure condition. So the way this is usually diagnosed is first clinicians will observe the behavior and try to figure out approximately what part of the brain might involve this region that's causing this type of epilepsy. And these are epileptic seizures that aren't treatable by any sort of medicine or diet or sort of less invasive interventions. What happens is an electrode grid is placed directly on the brain, like after the person gets a craniotomy, and they'll measure the patient for a series of days, usually not more than a week. And each one of these electrodes is effectively a time series, right? It's throwing off a signal. And you can actually start to think about these signals as forming the basis of a network, right? Each of these numbered electrodes becomes a node in a network model. that you can then apply some interesting analytics from and start to zero down into what is the part of the brain that is most likely causing epilepsy. It's an algorithm not unlike what Google does with PageRank. So this is a truly complex adaptive system because we're talking about the brain, right? The brain changes, the brain evolves, the brain actually moves, right? So from the time the clinicians diagnose what part of the brain might be causing the problem, the patient has then since been closed up and the brain may have shifted a little bit. So there's quite a lot of work in just narrowing down the geography in the brain of what region they're going to actually resect. But there's also a lot of collaboration amongst the doctors. It's not as though this measurement comes out and is just a perfect diagnosis, like just remove this 1 millimeter of brain. There's actually quite a bit of complexity. The process they use is not unlike a code review, it turns out, right? So they'll have these things they call grand rounds. Anybody in the medical field in here that knows what a grand round is? A couple of folks? Okay, so it's basically a conference of clinicians that will get together and they're looking at the data from EEGs or from tools like this one called EasyTrack, and they're basically arguing with each other and critiquing diagnosis like, oh no, I don't think it's exactly that part of the temporal lobe. It might be a little bit to the right. Are we going to resect the whole lobe? It's interesting to see this back and forth, right? You would think medicine's a lot more precise than that. That it's just like, oh well, we know exactly what to do. It was a little scary to me to see this process in action, but I found that there was a lot in common with what we were actually doing as engineers, right? So at Uptake, I joined Uptake mainly because of its reputation. At the time I joined, it's about 1.5 years ago. Its genesis was from Brad Keywell, who was one of the co-founders of Groupon, had a reputation for building these hyper-growth companies by looking for a really juicy problem that he could immediately build a sales pipeline around. And the way I put it is, they went the route of like, all steak and very little sizzle. Early on, even when I joined, the company was in pretty much stealth mode, right? If you went to their website, it was very hard to figure out what they were doing. But I heard enough through the grapevine that I knew it was going on. The time I came in, the company was about 2-ish years old. It had grown from 5 to 50 people in the first year. By the time I got there, I was around 200s, and then when we ended the year, it was around like 500. Now we're north of 700, right? And it's a mix of business and product folks and engineers. But anytime a company grows that fast, you got to be wondering, like, well, how do you even keep track of that, right? Like, how do you keep track of the org chart? How do you keep track of the architecture? How do you keep track of the teams? It turns out these are all pretty hard problems. And it's interesting that the same techniques you use to model epilepsy networks in the brain can actually be used to model systems. So I'm going to make the claim that looking at systems through a lens of network analytics gives you the ability to apply some automated, rigorous, sort of not just qualitative but quantitative analysis of your code and your systems, going beyond just libraries or applications, but entire ecosystems of, say, microservices and Kafka topics and databases and the like, and users. And that these things enable modularity and agility. Right? These things, I will argue, are very tightly related. So a couple of weeks ago, I actually presented at an INCOSE conference. How many people know what INCOSE is? Without me first defining it. Just a few folks. Okay, that's good. Because one of my goals of this is hopefully introduce these two communities to each other, because I think we have a lot to learn from each other. The systems engineering community was introduced to me when I was at Lockheed, right? And it's a very interdisciplinary group. Generally speaking, they build very complicated systems. So when you're thinking of like, the Boeing 747 or a locomotive like the engine or medical devices, there's usually a systems engineer in the loop there somewhere that's running some sort of simulation, that's doing end-to-end verification and validation on these things. There's a very close relationship with the way these folks work and the way we work in agile software development, but the two communities are very diverse and they don't often overlap. As you saw, there's only a few people that raise their hands. So INCOSE is the International Council of Systems Engineers, and already we have like a naming conflict, right? Because it's one of the hard problems of computing, naming things. There's systems engineers that are the type that write Chef and Puppet or the like on a day-to-day basis and are really working at the level of infrastructure automation. There are systems engineers that are running network cables, and there are these systems engineers. So when we say systems engineer, what do we actually mean? Well, I'm talking about the kind that are looking at end-to-end system design, right, and looking at properties of the system, looking at the structure of the system. And that was a technique I learned to do earlier in my career, and I just took it with me everywhere I went. And it always surprised me when people looked at me strangely and had no idea what I was talking about. So partly I have selfish motivations for giving this talk so that people don't do that anymore. So the talk I gave at the Systems Engineering Conference was in language that they understand, right? So DSM is the dependency structure matrix, and we'll see it in a little bit. DSM came out of work done in like, let's say, the early 80s, even earlier, really, but came kind of popularized in the 80s. And a book was published only a few years ago about how to apply dependency structure matrix techniques. Let's before we get into the details of that, let's talk about what is a system in general, right? What differentiates a systems engineer from people working on just parts of the system? I think the most important point to understand is anytime we have a series of interconnected parts, when these parts can represent people, they can represent hardware components, they can represent things like EC2 instances, Kafka topics. Think of those either people or agents acting on behalf of the system, or engineered artifacts of the system themselves that have some pattern of interactions, right? There's some innate dependencies amongst these things. In a physical system, it might be heat transfer or electrical flow. In an information system, it might be data flow. Your Maven POM for the Java developers out there, right, is loaded up with dependencies. Those can be treated as nodes in a network. And an argument from the systems engineering community is that the value of the system is in this emergent behavior that we get when these things come together, right? It's not just the parts, it's the relationships among the parts. So everybody knows that expression, like, the whole is greater than the sum of the parts. This starts to get into the quantitative aspects of that. So let's look at a library, right? So how many closure programmers do we have? A few folks? Okay. So one of the libraries we're going to look at is something I wrote called line topology. It's a Leiningen plugin that lets you take a closure project and parse the code and basically dump the function dependency structure, and we'll see what that looks like. Normally, if we look at a closure project, or any project for that matter, if I open a project I haven't seen before, one of the first things I'll do is just run tree. Right? How many people have not seen tree? Or will admit they haven't? Okay, it's a few folks, it's fine. It just basically gives you the directory tree structure. So this is a small project, just a few files, but it's a list, right? I have no idea a priori what the relationships amongst these things are. Just getting a list of files that are there. Not super useful. If I opened up one of the files, right, I could drill in. Now I'm looking at the list of functions that are in this namespace. For me to tease out the relationship, I've got to look at things like, okay, well, what requires do I have? And I could, traverse through my IDE and start looking at the function implementations and all that, and that's, that's pretty much the state of the art. What I haven't found is a tool that would just give me at a glance, like, look, here is your system overview. Here is your map of how all this stuff links up together. And that's what I started going after. And I was lucky enough to be able to have the opportunity to do this with 8th Late. Starting a few years ago, there was a program they started called the Master Cohort Program, where they brought in speakers to teach a class and have 10 or so folks go through a one-day workshop on a topic of the speaker's interest. Of course, mine networks. And so, a few people in this room are probably in one of my classes. And we geeked out on really getting into the details of how you would rip apart this code base and start to look at a really rigorous level of what the function dependencies are, right? And the analogy I give is, because we don't have this map, like we are navigating, right? We're navigating through this information space instead of this geography. Anyone who this is a depiction of? Anyone have a guess? Sacagawea, yeah, good. So Sacagawea, for those of you who don't know, was a Shoshone woman who was part of the Lewis and Clark expedition in the early 1800s, put it around 1804. Interestingly, one of the main reasons she was brought along was that the Lewis and Clark expedition was extremely dangerous. The map of the United States at the time of this expedition looked something like this. I can't know if it was exactly this, but at the time, the United States as we know it was this green blob. That brown blob was the Louisiana Purchase, right? It wasn't just the state of Louisiana as it is today. It was this huge swath of territory that the French owned, that Thomas Jefferson brokered a deal with and purchased. And Mexico was I think we were actually in Mexico if we were in 1804, or Southern California was still part of Mexico. So what happened was they started off in St. Louis and made their way, their goal was to make their way to the Pacific, following the rivers that were known to exist. People knew that fur traders and whatnot had been there. They knew the Pacific was out there somewhere. They just didn't have a map. What they had were anecdotes, right, of people writing down stories about how they traveled along. And so this was an interesting artifact that I ran across. It's called a gazetteer. So this was a series of books that were out around that time that were basically these stories that had been captured by explorers of a given area. So this is the Western States and Territories, where Illinois, where I'm coming from, was just a territory. It wasn't even a state yet. And in gazetteers, you would see this, it might be a little hard to read, but you don't have to read it all. But you would see this, little blurb, not unlike a Zagat guide that we have today, right? To go find a good burger in LA or something. In this case, where would I find, a fur trader, near the Mississippi River around St. Louis? You could find a little town of Cahokia, where, amongst other things, the inhabitants confine their attention chiefly to agriculture, but not with much spirit. So there's this little series of anecdotes, but there's a post office and a chapel for the Roman Catholic worship, and the seat of justice for St. Clair County, right? So there are these little landmarks that were put in these stories that were just captured in these books. We navigate our systems through these stories, right? We have practices like pair programming, so we can share knowledge amongst one another, or we write up diagrams in lucid charts or something like that. But it turns out now it's a lot easier to go find the old church in Cahokia. It's still there, apparently. I haven't been there myself, but Google Maps told me it's there. Now I can just navigate right to it, right? So what I kept wondering for a while now is where is the Google Maps of my code base, right? How do I just navigate a code base and just treat, in the same way that under the covers, Google is really treating cities and landmarks as nodes in a big graph and the roads between them as edges. What if I did the same thing with code? And so these experiments kind of evolved. This is a depiction of the line topology library itself, rendered with some technology that I'm going to show you. It's a mix of some Python code. It's a mix of a tool called SiteEscape. And then there's a little bit of art, right? And just laying out something that I think looks nice in the same way that a topographer or cartographer rather lays out a map. But what it tells you is a few things. I know it's hard to read, and it doesn't matter what the details are really. But the point is, if you and I were going to work on this code base, we'd be able to sit down and orient each other. Okay, so here's the thing. We're now, the symbols namespace calls closure zipper. You can see the symbols namespace is off on the right there in blue. It's nicely encapsulated. The zipper implementation is a little hard to follow. I think we can simplify it a little bit and make it a little more intuitive. We're basically going to rip that namespace out and replace it. It's a nice trigger for a conversation, right? It's just a nice visual cue. I could show you that in the code too, but there's a little bit higher a barrier to entry, right? It's the same as the length of time it would take you to read the gazetteer versus going to Google Maps, right? What's that instant feedback loop like? How valuable is that for you? So going back to that definition of architecture, the structure is really, in this case, it's represented by this model. Each one of these nodes represents a function, and the functions that function in turn calls. These namespaces, in some cases, were created because I was explicitly trying to create hidden modules, right? The ability to change the system and hide implementation details. So the definition given in this systems engineering book, the Design Structure Matrix Methods and Applications, very interesting book that came out just a few years ago. So for those of you who are interested in this stuff, this is definitely a resource worth looking at. It's a very precise definition, right? Because it starts getting into a mathematical model that we can use to not just qualitatively talk about this stuff, but actually start writing some code that does it for real. So I started thinking about this systems interpretation as a graph or a network. There's an interesting quote in a generic book about just analyzing any kind of network data, where you start to see some insight that this gives you, right? That you can rephrase questions you have about a system in a language of network science or graph theory, and suddenly have this scientific and mathematical backbone to ride on, to reframe your question into something that can be rigorously solved, that goes beyond the level of just opinions or anecdotes, but gets down to okay, can we actually quantify this, and let's have a rational discussion about this. I think of it as making a principled argument, right? I'm stating a case that this system is more modular, and there's value in pulling this module out, and I can show you why I believe that to be true. It's not just my opinion. So here's how you start. If you're thinking about, let's say closure, as that's going to be our working example, but it would apply to any language really. If we have function A making a call to function B, A depends on B, any artifacts we have in the system, whether it's a function call or a microservice call, did we lose the picture? It's back, good. Whatever kind of dependency we have between our engineered artifacts, at the end of the day, our network model is super simple, right? It's vertices and edges, and we can have some properties on our vertices and edges. There's direction in the sense that a dependency is not two-way, right? So if I depend on Rails, Rails does not necessarily depend on me, luckily for them. And this is the essence of architecture. Now we can reframe a question like, how many people have heard of coupling and cohesion, right? Those terms. It's a fairly common term, right? So in general, if we were to rephrase the notion of a coupling cohesion to say we want our systems to be loosely coupled and highly cohesive, well, how do we go beyond that quality, Well, okay, it's few dependencies between modules, and cohesive means the dependencies we have are within the module, right? So we want common things to be related to one another. If we think about the social ramifications of that, right? Why is that valuable? Well, if this group over here is building one library that I depend on, and this group over here is building another library, if they have dependencies between themselves, then they've got to go have a meeting about how they're going to manage the interface that they need to change that's exposed to me. Now I have to come to the meeting. And what if every table in here represents a part of the system, right? How many meetings are we going to have to maintain the interfaces? As opposed to if we've figured out how to hide parts of the room from one another, right? And said, here's your interface to this half of the room. Here's your interface to this other half of the room. We've immediately cut down the number of meetings. And that's just one side effect, right? It's the human time side effect. So I know we're getting pretty abstract. Brian Merrick is a great inspiration here. He always throws this one out, and it's really getting like pretty high level. Let's see some code. So let's do that. So let's look at, if we want to look at line topology, let's first look at how you run this thing. So here I am. Can you guys see that? Look okay? So this is within line topology itself. I can actually just run the command line topology because I have the plugin installed. So what this thing is going to do is go through each of my files, read them in, apply some magic for now, let's just say that, to figure out what the fully qualified namespace is of each function. And then when a function calls another function, every time that happens, I'm going to increment a weight. So for each line, I've got a source, a target, and a weight. So you can see, for example, in this one, in the symbols namespace, the seek map zip function calls closure core's map function twice, right? Now, on its own, this isn't very useful, right? But this is our raw data that we'll need to do more interesting things. There are a lot of things you can do with this data, right? You could run it through something like Graphiz, and there are plenty of closure plugins out there that will do something along those lines, right? They'll give you a visualization, they'll give you the output. What I wanted to do was just get the data. There are a lot of ways I can visualize network data or that I can compute on network data. I just wanted the data. So line topology does one thing and one thing only, spits out your dependencies. Now that you have them, you can use some other techniques. I'm using a library called PyDecideEscape. For those of you who want to look this up later, Siteescape.org is the place to start. It's a free open source visualization toolkit used by the systems biology and network biology community. Here, I think this is probably a protein interaction network or a gene interaction network. So they're using this to visualize very large scale networks, tens of thousands of nodes, hundreds of thousands of edges. They've built some really sophisticated visualization technology to allow that to be possible. And it's rock stable. It's very stable compared to other libraries I've used that I won't name. So let's see what we can do with this. How many people have used Jupyter Notebooks? Okay, nice. So this is another one that I think we can steal from other communities here. So within the data science community, Jupyter Notebooks are fairly de rigueur, right, as are other types of notebooks. There's an R equivalent with Shiny. What this lets you do is combine documentation and a REPL, right? So in this block here, and we could have a whole talk just on Jupyter, so I won't spend too much time on this, but here I have Markdown, so I can get some nice documentation. And here I have actually a Python REPL. So I'm evaluating some Python code here. Here I'm going to read in my network data that I just generated. I saved that off to a file. I'm reading it in as CSV, and I'm going to save this in a list of dictionaries. So now you can see like our source, target, and weight nodes. And now I can use a library called iGraph to read this in. This is basically an in-memory graph computation library. And you can see some stats that it spits out. It's saying I have a directed network with 107 nodes, 206 edges, and showing some attributes that have been computed. We want to make sure our data is simple in that, simple meaning it doesn't have multiple edges between the vertices and it has no loops, which is a pretty good definition of simplicity in really any context, but here it has specific mathematical meaning. And now we're going to do some clustering. Now clustering in this context, we'll see different clustering later, but in this context, we really mean like namespaces, right? That's a way to think of a cluster. It's a group of things in general, but here we're talking about a group of functions within a namespace. So we can see that this library SAN that I've written in Python created some of these things for me. But out of the box, it's not very useful. It just uses the label to just say, hey, here's a default. We'll just say the label is a namespace. 107 namespaces, though, would not be good. So we're going to actually just use the actual namespaces we have. That gets us down to 20. Now we can filter things out. We can compute the degree distribution of this network. What this is telling you is there are a fairly large number of nodes that have only one connection, or maybe two, as we go down. And then there are a few nodes that are much more highly connected. Now, why is that important? Well, if we look at this out degree and in degree, i.e. Efferent and afferent coupling, as it's sometimes known, we can see that in some cases we have a max in degree of 13, a max out degree of 15. So I could say, like, well, if I take 80% of that and just try to look at what vertices are higher than that number, well, in this case, I might see, some of my topology namespaces as things that have maybe a high number of dependencies that I might consider splitting. I could see what things will impact the system. In this case, I'm actually looking for something to filter out. There's a lot of closure core in here, unsurprisingly, right? Because it's the basis of the language. So I want to filter that out. I'm not going to want to visualize closure core. So again, computationally, I can filter that out and end up with a much smaller network of just a few vertices. And now here's where it gets cool. This is what sold me on Cytoscape. So when you start Cytoscape up, it's a desktop app, but it also starts a little RESTful server behind the scenes. So what that lets you do is use, in my case, the Pi to Cytoscape library to connect to that API through the Jupyter Notebook. Now I can start driving this visualization programmatically. And the reason that's important is as the system changes, I'm a programmer, right? I'm lazy. I don't want to redraw my diagram all the time. Who uses Lucid charts on a regular basis? Okay, a few folks. I have nothing bad to say about Lucid Chart. It's a beautiful tool. It is rather time consuming to maintain diagrams that represent systems that frequently change, right? So to the extent that we can start to automate this, it gets kind of interesting. So here I can apply something like a force-directed layout. I can define a custom style that will do things like, add our labels in. I can change the colors of the nodes. When I apply that style, it starts to look more like the thing you saw before. And then I can, start to manually move these things around. I can tweak them. And so, early on, that's exactly what I did. And so now I can just simply restore that layout. So the cool thing about this is as this code is changing, if I want to maintain this map, maybe on every successful build or something, I might have something like new nodes off to the side and then just kind of lay them out. What this lets me do is see things like I just sort of take it to the convention that tests are off to the side. Tests are now hitting, certain key parts of the system where I know like this is sort of an internal hub that feeds a bunch of these smaller namespaces. I know this entry point here is where lining itself calls. So there's actually not much code here. This is more interesting, and so I've got a lot of test coverage there. I'm testing the integration points, right? So these are unit tests in terms of their implementation. They're closure tests, but they're acting as integration tests. I don't have a lot of tests on some of the finer grained namespaces. The minute I wanted to change them, though, I would create one. Right? I want to test the interfaces. Okay, so we can do things. I won't go into all the details here. We can generate SVG exports. That's all fun. It's all nice. Let's get back to what we were talking about earlier, though, this idea that there's a parallel between the network and a matrix. So if you really want to go to the next level and automate everything, and you don't want to manually lay out anything, a matrix view is an option. This is using a library called Bokeh that does some interesting visualizations in JavaScript. You can export these as static sites, it turns out, or you can view them right in the Jupyter Notebook. So for each one of these edges, I'm basically following on and saying anything in the row depends on the thing in the column. So if I'm sorting by in degree, you can just sort of see at a glance the highest in degree things are going to land on the left side. Right? So once you know how to read this stuff, and this goes back to that DSM book, you just start to get some pattern matching here. Like you can take any system, run it through this, and just take at a glance, kind of look at the matrix. The coloring is showing you dependencies between libraries, so it's colored gray if it's a dependency between a module, and it's going to be the same color if it's a dependency within a module. So if we do something like sort by group, again, we get that sort of pattern matching of like, well, just at a glance, right? You just sort of squint, like how much coupling are we going to have? Now that's the qualitative aspect of it, right? But I told you we could quantify it. Well, without going into too much detail here, suffice to say, if I want to really get rigorous, like what does it mean to say you have high cohesion? Well, because I'm treating it as a matrix, right, I can say there's n squared things. If I have n nodes here represented in this square matrix, then it's n times n for the size of the matrix, yeah? That's what this is saying here. It's saying for each module you have, take the square as its score of like, this is its module, the score of that module, and just take the sum of those squares. And optionally, you can multiply it by some coefficient. And you're going to add that to the number of calls between modules, right? This is now an objective function, right? This is a mathematical way of representing something that you can now code up to say, how would I score the modularity of a system? And when I saw this, I thought this was kind of cool, right? Because now my head goes into like, all right, so let's start getting into like predictive analytics kind of stuff. Can I like have some kind of machine learning algorithm optimize my modularity for me? Probably. I haven't tried that yet. But let's just look at the scores really quick about how you can do this stuff. If I just filter on the topology stuff, if I run the objective function that's built in this library, I get some sort of arbitrary score. 121, what does that mean? Well, let's look at the range of possibilities. One extreme in any system, right, would be to split everything into its own namespace and everything as one function, right? Then we would get a heavy tax on the number of intermodule calls. So it'd be pretty extreme if this were a company and every single one of you were your own manager in your own department. Like, that's a lot of administrative overhead intuitively, right? The other idea would be it's a completely flat organization. Nobody's in charge. Everybody is in the same department. We're all one team. And similarly, you could put all your functions in one namespace, one big fat namespace. I've seen code bases like that. And intuitively, there's something wrong with that too, right? It's like, well, everything's kind of disorganized. It seems like it's all related, but it's really not. Well, that's where your square will come in, right? You'll get penalized for having this large squared number. So that gives you the kind of range of like, well, now I could say, what is an upper bound of, this sanity check? How close am I to the insane of one extreme or the other? And so this now gives you a way to start looking at like, okay, well, a score of 121 compared to 361 at one extreme and 199 at another extreme means the modularity that's there is somewhere looking kind of good. Compared to what, again, though? Now we can do things like run community detection algorithms to start looking at, well, algorithmically, what would the structure of the network give us absent the domain, right? Without knowing anything about what this thing represents. From the structure of the network alone, given the dependencies that are there, what communities appear to be there? So in this case, there's an algorithm called edge betweenness that spits out 4 communities. We won't get into how you can do things like then visualize that and say like, okay, how might I rearrange this thing to actually look that way? In my case, the number that spits out when you score the edge betweenness, 133, is higher. You're trying to minimize the subjective function, by the way. This score is higher than the modularity I already have. So I'm going to infer that the modularity I have is superior to one that I could algorithmically create and superior to the extremes. It's all sounding kind of dry, I know, but trust me, it's going somewhere. You're getting an algorithmic recommendation about how to improve the code, right? This is the kind of thing you can bake into a tool chain, right? This is the kind of thing you could put into a CI build and start spitting out a report on a build-by-build basis. How is the modularity changing over time? How is modularity varying across large numbers of code bases, maybe within your company, maybe across GitHub? How does that modularity score move along with other things? Like, for example, the number of contributors in an open source project. Or with other relative things, like maybe some subjective measure of code health. Maybe you just ask people, do you like to work with this project, and do you like to work with this other project? Is there any correlation between that and the modularity score? Having this objective function starts letting you build that data set and answer these questions in a rigorous way. Whereas if I didn't do that, right, if I just kind of had my opinions out there, I could write a blog post on it, and people do that all the time. I do it sometimes. But if you want to go to that next level and say, how would you make a principled argument, right? So you can start to make a scientific argument, an engineering argument about why this stuff exists. This is a step down that path. Follow me? All right. So, quickly review. The equivalence here is that the functions you write every day, it doesn't have to be Clojure, by the way. Any function you write, at the end of the day, is a dependency graph. It's just not necessarily explicitly treated as such. Interesting fact, I literally just found out, like this morning, GitHub introduced a dependency graph feature. So it now does things like parses your gem files or parses your Maven POMs, shows you the dependencies you have, and then starts adding value on that. Because dependencies by themselves, admittedly, don't seem to be very interesting. But what if you wanted to know the security vulnerabilities that have been exposed in those dependencies that by virtue of the fact that you're dependent on them, you are now exposed to, right? So like that's kind of getting you down the path. Like what can you do with this stuff? What are the applications? You could think of them all day, right? That happened to be the one they first implemented. We talked about this idea of like how to identify tests in the system. I've had this argument many times with many people. There are folks who will argue. Let me try to remain neutral. How many people? See, I blew it. Poker face, Bobby. How many people think 100% test coverage is a great idea? Now you're not going to admit it. I already blew it. But some of you do, and you're just not going to admit it. I get it. I will argue that 100% test coverage is not your goal. 100% test coverage at the interfaces with other systems is a valuable goal, right? Because now you can change these hidden subsystems, have a minimal number of tests to change, know that all the information flows at the end of the day are going to move through these central interfaces. And so as long as I have great test coverage there, I can refactor the internal implementation. And if my tests still pass, I haven't broken anything, right? Now, we can argue later about whether I'm right or wrong over a beer, but point being, this is a principled argument I'm making, right? And I can now point to this and tell you why I think that. So if you're going to argue with me about this, you have to bring a principled argument. Those are the rules. I'll remind folks of the famous mocks aren't stubs debate. This came up just recently, so this was a recent addition, top of mind. But zero deductible insurance is expensive, and when you extensively mock out every interaction of your system, when your tests look like this and the actual system also looks like this, it's a lot of overhead to maintain. When you refactor a subsystem you thought was hidden, and now you have to go refactor 50 tests, it feels like a tax, right? Because you're not necessarily getting any new value. Like, well, verify that this call happened. Yeah, it happened. But why did I even need to know that at the level of the test? On the other hand, a stub returns a known value. So if you're stubbing out a subsystem that might be a third-party service, right, and you're getting this result back that matches basically the contract you have with that third party, that could be extremely valuable, right? Because you're verifying, if you give me this response after I send these parameters, then I can carry on with my business. You just need to maintain that service or library or whatever it is that you have and maintain your contract. And I don't really want to know what happens beyond that. So we could start thinking about some network-centric software metrics, right? Reframing some of the questions that come up again and again about code quality and about how we measure productivity or how we don't measure productivity. I mean, I'd settle for this a simple question: how big is the system, right? There's the old lines of code. Like, we could use lines of code. Yes, and it's kind of the least worst thing out there, right? Like, it is a metric, and it can be insightful in context. It can be helpful to know, for example, how many lines of code maybe are in each module. It might be helpful if you're comparing at the level of like library. Like, yeah, a library that has 1 million lines of code is going to be different than a library with 100 lines of code. So orders of magnitude level that comes in. Much more interesting to me if you can tell me at the level of these vertices that I'm modeling, though, what the line of code count would be, right? I could even on that graph resize the nodes by lines of code if I so chose. I'm more interested in, for a given package or namespace, how many functions are there, though, and what are the calls? I'm more interested in modularity than lines of code, but I'll take it as something that I could use to decorate this network. I'd take test coverage of the module boundaries over test coverage of the entire system that is done ignorant of the module boundaries. And I would take documentation of the module boundaries over 100% documentation of the whole code base. Interestingly, you very rarely get a nice depiction of who is actually building different parts of the code, right? Usually in any sufficiently large code base, we don't work on the entire thing unless we're really rigorous about pair swaps and whatnot. But generally speaking, with any sufficiently large ecosystem, you'll just hit a certain equivalent of the Dunbar's number, right? Where Dunbar was a sociologist that said you could only know on average roughly 150 people and maintain stable relationships. I don't know exactly what the equivalent of that is in software. I don't know if that work's been done yet, but I'm going to guess that there is some cognitive limit there, that we can't know infinitely many libraries, right? And we can know more than one, so clearly there's something in the middle there. What is the equivalent of Dunbar's number there? I don't know, but I've hit it. I know I've hit it, right? Where I'm just like, I can't take anymore. Like, I'm just going to have to trust what you say about how your system works. Just tell me what the contract is. But I do want to know who to talk to, right? And it is interesting to me to look at the social network, and you can do things like on GitHub, look at the Git logs and see who's committed to what parts of the system. But let's look at something a little more familiar. How many Game of Thrones fans do we have? I like Game of Thrones. All right, so luckily, a mathematician at McAllister also liked Game of Thrones, and parsed Storm of Swords, looked at any time two characters' names appeared within 15 minutes of one another, treated that as an edge, and then every time that happened, just incremented the weight on that edge. Published a nice paper about it in one of the Scion publications, just to kind of get people interested in network science, and it's a cool paper to go read, but I wanted the data. I was like, just give me the data. I got my own little toolkit I can run against this thing. So I give you Game of Thrones at testedminds.com. So this guy lets you do some fun stuff. This is taking that data set. It's saying, again, from the network properties alone, you can start to compute things like who is the most central, let's state it purely in network terms. What is the most central vertex in this network? Well, centrality has a few definitions. Tyrion bubbles up to the top in several of those definitions. So he has the highest degree. This isn't directed, so it's just degree. He has the highest page rank. He has the highest betweenness, meaning shortest paths that cross him if you were to just pick shortest paths to the graph. and he's Tyrion. I mean, if you know the books, you know Tyrion. So intuitively, you already knew Tyrion was a main character, right? But what's cool about this is things like the community detection, right? This was just like I ran edge betweenness on this thing, and it bucketed these people into various groups. So if you look computationally, right? Again, no man behind the curtain here. This kind of looks like Daenerys' social network, doesn't it? Right? Like for those of you who know the books, like yeah, like these characters appeared close to one another. Like they're probably somewhat closely related. They probably also appeared in scenes together in the show. It's interesting to again imagine you take a code base that you don't know, run some computations like this, and instantly get a layout of like here are the high-level modules in this thing without you even digging into whatever people happen to name things, whether those names were meaningful or not. And some of it's just eye candy, admittedly, right? Like you click on one of these things, and this is leveraging the Cytoscape JavaScript library. So I'll give Cytoscape a little plug here because I really think they did great work. js.cytoscape.org will get you there. So I encourage you to go explore that if you think this stuff is fun. They did a lot of nice visualizations here, very practical ones where you can start seeing paths, some fun ones. But I found this, a nice way to kind of play with a data set that was completely agnostic to software using exactly the same workflow. So the same thing I showed you before, this is all open source. You can find it in the Tested Minds GitHub account. You'll see very similar code that I use to analyze the system data, used to analyze the social network. And so, just sort of illustrates that point. Like the notion of network science is inherently domain agnostic, right? We're able to leverage just the generic mathematics behind network properties and start applying those to the domain of software, right? And you need to interpret them in the context. So you in this case, PageRank means something different in the context of web pages versus in the context of social networks versus in the context of engineered software systems. But it does have an interpretation, right? The metric is still there. There is something the network structure is telling you. So I spend a fair amount of my day collecting the dots and connecting the dots and automating these things, right? Where I'm looking at how I can make the architecture of a system as visible and as attainable as possible, and in as automated a way as possible. Because again, I don't like to sit and update diagrams manually all the time. So you can find again on GitHub a few of these things. I was inspired early on, and maybe I got some of these history questions right on the Jeopardy stuff because I do tend to like history of computing. This is Friedrich Bauer. He was one of the members of the NATO Science Committee that sort of founded the term software engineering back in 1968. And when he was talking about the dynamics of software development, and he has this quote, right? What's needed is not classical mathematics. What he kind of meant by that was the calculus and the sort of closed form, symbolic manipulation that was available at the time, but rather, this new kind of mathematical thinking about systems, given that network science, as I'm talking about it now, wasn't really defined until the 90s, right? So 30 years ahead of that, here he is kind of feeling the need for this kind of vocabulary, and it just wasn't there. Or if it was in sociology communities or economics communities or corners of the physics community. There wasn't one central place you could go. So I think the goal of this is really to bring diverse communities together, right? So get systems engineers, get software engineers, get network scientists talking. The data that we could collect out of GitHub becomes interesting to the network science community, who's looking for more of these properties like edge betweenness or PageRank that apply to many kinds of networks. In turn, the insight we get from the network science community can be turned into algorithmic tools that we can use to analyze our systems better, like Cytoscape, for example, that came out of network biology. And then it gives us a new vocabulary to use to really rigorously and principally kind of describe what it is we're doing that right now is oftentimes just high level, very qualitative. There will always remain an aspect of craftsmanship, right? I think what I'm arguing is we can start to apply that style of craftsmanship to a new domain, right? We can start to think of architecture as something that can be crafted, not just the nodes, also the relationships amongst the nodes. So I would encourage you to reach out to me if you have any interest in this stuff. I'm actively looking for people to basically build edge collectors, right? So I've parsed Clojure, but to the extent we can start parsing Python, Java, any language you can think of, becomes really interesting. Parsing things like consumers and producers to Kafka topics becomes really interesting. So if you have any interest at all in working in that kind of stuff, please reach out. And with that, thank you, and have a great conference.